Section: Introduction. In this section, we discuss the advancements in deep reinforcement learning (RL) and its impressive results across various fields, such as board games, online games, language models, robotics, and drone racing. These achievements highlight RL's ability to match or exceed human performance and its unique capacity for scaling and generalizing through autonomous exploration. Given this potential, we aim to use RL to tackle complex dexterous manipulation tasks using vision. However, the successes in this area have been limited. Previous research has shown that highly dexterous manipulation cannot be easily programmed or controlled by humans, but these methods often focus on specific skills, which restricts their broader use. To understand why RL isn't more widely applicable to vision-based dexterous manipulation, we first identify the unique characteristics of dexterous manipulation that set it apart from other applications. We then explore how these characteristics create challenges for applying RL algorithms and develop new techniques to overcome these obstacles. By combining our insights and methods, we propose a framework for applying SIM to real RL to humanoid manipulation tasks and present promising results. We outline several key challenges and our strategies to address them. The first challenge is environment modeling. It is difficult to create a simulated environment that accurately reflects the real world. While real-world RL avoids this issue, training with physical hardware requires high-quality equipment, maintenance, and safety measures. With complex systems like humanoid robots with multi-fingered hands, real-world exploration becomes even more challenging. Simulations, on the other hand, allow for unlimited trial and error, which drives the development of SIM to real RL methods. We suggest an automated reel-to-SIM tuning module to reduce the engineering effort needed to bridge the environment modeling gap. The second challenge is reward design. Crafting a reward function to guide RL policies is notoriously difficult, especially for manipulation tasks that involve many contacts or long durations. Previous approaches often rely on expert knowledge, which limits scalability. We propose a new principle for designing rewards by breaking down tasks into intermediate, contact goals, and object goals, using a key point-based state representation for contact goals. This approach allows us to learn complex tasks, like bimanual handover, from scratch. The third challenge is policy learning. Even with a well-defined reward function, learning effective RL policies can be tough due to the complexity and sparsity of rewards in high-dimensional spaces. The diverse contact patterns in dexterous manipulation further complicate this. While unsupervised methods have been suggested to promote exploration, they don't fundamentally solve hard exploration issues. We address this by introducing two techniques: starting tasks with informed hand poses and breaking down difficult exploration tasks into simpler subtasks, training expert policies for these, and then combining them into a general policy for the full task. Our experiments show that these methods enhance learning efficiency. The fourth challenge is object perception, which is crucial for manipulation since it involves interacting with various objects. The vast diversity of objects in terms of shape, size, and other properties makes this a long-standing issue. The application of SIM to real RL in dexterous manipulation is hindered by the need for expressive object representations, which can widen the SIM to real gap. To tackle this, we recommend using a mix of low-dimensional and high-dimensional object representations, applying specific data augmentation to the high-dimensional features to minimize the perceptual gap. We systematically investigate how this combination can balance learning dexterous manipulation policies and transferring them effectively to real robots. The strategies we have outlined create a comprehensive approach for SIM to real RL in vision-based dexterous manipulation. We demonstrate successful learning across 3 dexterous manipulation tasks on humanoid robots and conduct thorough ablation studies. Section Summary. In this section, we explore the challenges of applying deep reinforcement learning (RL) to vision-based dexterous manipulation, identifying key issues such as environment modeling, reward design, policy learning, and object perception. We propose novel techniques to address these challenges, including automated reel-to-SIM tuning, a new reward design principle, task-aware initialization, and a mixed representation approach for object perception, ultimately outlining a comprehensive strategy for effective sim to real RL in this domain. Section: Background. In this section, we discuss the background of our work in deep reinforcement learning (RL) applications to robotics. The recent successes of deep RL in various fields have generated significant interest. However, we have observed that this approach can be fragile, particularly due to its sensitivity to hyperparameters and issues with reproducibility caused by the inherent variability of RL algorithms. One of the most pressing challenges in RL is exploration. Unlike supervised learning, where data is readily available, RL agents must gather their own data and adjust their strategies based on what they collect. This data collection issue is known as the exploration problem. In real-world robotics, where we deal with complex observations and dynamics, along with often sparse rewards, exploration becomes even more difficult. Although some methods have been developed to enhance exploration in high-dimensional spaces by promoting visits to new states, they do not fully solve the exploration issue. Additionally, applying RL to real-world robotics highlights significant challenges that standard RL benchmarks do not address, such as poorly modeled environments and unclear reward functions for specific tasks. Previous research at the intersection of robotics and RL has suggested various practical solutions, like learning from human motion data or teleoperated demonstrations, and using real-to-sim techniques to better model environments. While some of these methods may overfit to particular tasks, they provide valuable insights that inform our work. When it comes to vision-based dexterous manipulation in humanoids, we note that advancements in teleoperation and learning from demonstrations have led to progress in this area. However, training teleoperators to gather high-quality manipulation data can be expensive, and the amount of data needed to achieve human-level performance can be prohibitively high. We have seen that several existing studies have successfully applied RL to dexterous manipulation with multi-fingered hands, but many either focus on a single hand setup or do not utilize pixel inputs for object representation. Most of the current research tends to concentrate on individual manipulation skills, such as in-hand reorientation, grasping, twisting, and dynamic handover. The work by Chen et al. Is the closest to ours, but it relies on human hand motion capture data to learn a wrist controller instead of developing full hand-arm joint control from the ground up. Furthermore, many existing studies focus on hardware that has been extensively tested in physics simulations. Our work is unique in demonstrating successful transfer of vision-based dexterous manipulation policies from simulation to a new humanoid robot with multi-fingered hands. We identify 4 key challenges in applying sim to real RL to dexterous manipulation and outline our strategies for addressing each challenge. We will detail our specific approaches in the following sections, supported by an overview of the challenges and our methods. Regarding real-to-sim modeling, we recognize that simulators provide unlimited opportunities for trial and error, which is essential for exploration in RL. However, the successful transfer of policies learned in simulation to the real world relies heavily on how accurately we model both the robot and its environment. In dexterous manipulation, this modeling challenge is intensified by the need to represent objects, which can vary greatly and whose physical properties are not always easy to quantify. Even when we assume we know the true physical parameters, aligning simulation with reality is challenging. This is because the same physical constants used in both environments may not yield the same kinematic and dynamic behaviors due to the limitations of physics engines. To improve modeling accuracy, we propose a practical technique called the AutoTune module. This module accelerates the real-to-sim modeling process by quickly calibrating simulator parameters to match the behavior of real robots. It automatically searches for optimal values for both simulator physics and robot model constants in under 4 minutes. The AutoTune module works with 2 types of parameters, those affecting kinematics and dynamics in the simulator, and robot model constants from the URDF file, such as link inertia and joint limits. The calibration process starts by initializing multiple simulated environments with randomly sampled parameters based on the manufacturer's robot model. It then runs calibration sequences on both the real robot and all simulated environments simultaneously. By comparing the tracking errors, the module identifies the parameter set that minimizes the mean squared error in performance. This method streamlines the tuning process, requiring only one set of calibration runs on the real robot and allowing for the simultaneous evaluation of multiple parameter combinations. For object modeling, we find that representing objects as simple shapes, like cylinders with varied parameters, is effective for learning transferable dexterous manipulation policies. Our approach adopts this strategy and proves to be successful. Section Summary. In this section, we discuss the challenges of applying deep reinforcement learning (RL) to robotics, particularly the exploration problem and the difficulties in sim-to-real transfer due to modeling inaccuracies. We introduce our Auto-Tune module, which automates the calibration of simulator parameters to match real robot behavior, significantly speeding up the modeling process and enhancing the reliability of RL policies for dexterous manipulation tasks. Section: Generalizable Reward Design. In this section, we discuss generalizable reward design in reinforcement learning (RL). The reward function is essential as it shapes the agent's behavior. However, much of the current RL research has focused on developing learning algorithms while treating reward signals as fixed. As we tackle more complex tasks, especially in robotics, designing effective reward mechanisms becomes increasingly important and challenging. For dexterous manipulation with multi-fingered hands, the variety of contact patterns and object shapes complicates reward design. We notice a common pattern in human manipulation. Each task can be seen as a series of hand-object contacts and object states. Based on this, we suggest a general reward design approach for long tasks involving rich contact. We break down each task into a sequence of contact and object states. For instance, in a handover task, we can identify steps like one hand touching the object, lifting it, the other hand making contact, and finally transferring it to the goal position. We define rewards based on contact goals and object goals. Contact goals can be set by penalizing the distance from fingers to desired contact points or the object's center of mass. Object goals can be defined by penalizing the distance from the object's current position to its target position. To simplify specifying contact goals, we introduce a keypoint-based technique where we generate contact stickers on the object's surface, representing potential contact points. We also address sample-efficient policy learning. Given the complexity and sparsity of rewards in high-dimensional spaces, especially with humanoid robots, learning policies can be time-consuming. We propose two methods to enhance sample efficiency. 1. Using task-aware hand poses for initialization, and 2. Breaking down complex tasks into simpler subtasks and combining their specialized policies into a generalist policy. For task-aware hand poses, we gather data from human operators using a teleoperation system, allowing us to collect useful hand pose data quickly without needing complete task demonstrations. This significantly reduces the time required for data collection. In our divide and conquer approach, we suggest breaking down complex tasks into simpler ones, allowing us to train specialized policies for each subtask. We can then distill these into a generalist policy, filtering out only the best trajectory data for training. This method aligns closely with learning from demonstrations, where subtask policies help gather data in the simulation, and the generalist policy is trained on this curated data. Section Summary. In this section, we discuss the importance of designing adaptable reward mechanisms for reinforcement learning (RL) in complex tasks like dexterous manipulation, proposing a scheme that breaks tasks into contact and object goals to simplify reward specification. We also introduce techniques to enhance sample efficiency in policy learning by using task-aware hand poses for initialization and dividing complex tasks into manageable subtasks, allowing for the distillation of specialized policies into a generalist model. Section: Vision-based sim to real transfer. In this section, we discuss the challenges of transferring a policy learned in simulation to the real world, particularly in vision-based dexterous manipulation. The sim-to-real gap arises from both dynamics and visual perception, which are complex issues we aim to address. We highlight two main techniques we use to bridge this gap. First, we mix object representations. Object perception is vital for dexterous manipulation since it involves interacting with objects. Previous research has shown that successful sim-to-real transfers have utilized various object representations, ranging from simple 3D object positions to more complex RGB images. There is a trade-off. While higher dimensional representations provide more information, they also increase the sim-to-real gap, making policy transfer harder. Conversely, lower dimensional representations offer less information, complicating the learning of optimal policies. To balance these trade-offs, we propose using both a low-dimensional 3D object position and a high-dimensional depth image. The 3D position is captured from a third-view camera to ensure consistent tracking, while the depth image provides additional geometric information. Second, we employ domain randomization for both dynamics and perception to enhance reliable sim-to-real transfer. We provide further details in the appendix. Our proposed methods create a general framework for applying reinforcement learning to dexterous manipulation tasks with humanoid robots. In this section, we present experimental results showcasing task capabilities and conduct ablation studies for each technique. Videos of our experiments are available on our project website. For our experiments, we utilize a Fourier GR1 humanoid robot equipped with 2 arms and multi-fingered hands, each arm having 7 degrees of freedom. We primarily use the Fourier hands, which have 6 actuated and 5 under-actuated degrees of freedom. To demonstrate cross-embodiment generalization, we also include results from the Inspire hands, which have 6 actuated and 6 under-actuated degrees of freedom. The hardware varies significantly in mass, surface friction, and morphology. In terms of perception, we combine dense and sparse object features for policy learning in both simulation and real-world settings. We set up an egocentric view camera on the robot's head and a third view camera on a tripod in front of it. In simulation, we calibrate the camera poses to match those in the real world. The dense feature is derived from depth observations, while the sparse feature approximates the object's center of mass using the third view camera. We utilize the segment Anything Model 2 to create a segmentation mask for the object at the start of each trajectory and track it throughout the sequence. We calculate the 3D center of mass coordinates by finding the center of the masks and using depth readings to obtain the corresponding 3D position. This perception pipeline operates at a frequency of 5 to align with the neural network policy's control frequency. We define several tasks for our experiments. In the grasp and reach task, the robot uses one hand to grasp an object, lift it, and move it to a designated goal. A scripted visual module determines which hand is closer to the object at the start. The objects vary in shape, mass, volume, friction, color, and texture. In the box lift task, the robot lifts a box that cannot be grasped with one hand, with variations in color, size, and mass. We randomize the initial position and orientation of the boxes for each trial. Lastly, in the bimanual handover task, the robot grasps a block with one hand and hands it over to the other hand, with variations in the block's colors, dimensions, and masses, as well as their initial positions and orientations. Section Summary. In this section, we address the sim-to-real transfer challenges in vision-based dexterous manipulation by employing a combination of low-dimensional 3D object positions and high-dimensional depth images to balance information richness and transferability. We also utilize domain randomization and a structured perception pipeline with dual camera setups to enhance policy learning and validate our approaches through various manipulation tasks with a humanoid robot. Section: Evaluation of real-to-sim modeling. In this section, we evaluate the effectiveness of our auto-tuned robot modeling. We utilize the auto-tune module to identify the best parameters for robot modeling. To assess its effectiveness, we compare the success rates of transferring policies from simulation to real-world scenarios using 3 different sets of policy checkpoints. All policies are trained under the same conditions, but they use different parameters that result in varying levels of mean squared error, from the lowest to the highest. Our results indicate that auto-tuned modeling enhances the transfer from simulation to reality. Additionally, our video showcases successful transfers of grasp and reach policies to the Inspire hands, highlighting the versatility of our auto-tune module. Next, we examine the effectiveness of modeling objects as simple geometric shapes like cylinders, cubes, and spheres. We find that this approach balances training efficiency and transferability well. Our comparison of training curves shows that policies using primitive shapes are more sample efficient than those using complex shapes. Moreover, policies trained with randomized primitive shapes can adapt to various unseen objects, as demonstrated in our video. We also evaluate our reward design principles, which enable a wide range of complex tasks to be performed using pure reinforcement learning. The learned policies show high dexterity and resilience to random forces. We visualize different contact behaviors in the box lift task, revealing that these behaviors align closely with the specified contact positions, confirming the effectiveness of our contact markers. In terms of policy learning, we assess the impact of task-aware hand pose initialization. Our findings indicate that incorporating human priors significantly enhances exploration efficiency in challenging reinforcement learning tasks. We further evaluate our divide and conquer distillation method through 2 studies. First, we analyze how the granularity of task division affects training efficiency by breaking down a multi-object grasp and reach task into subtasks with varying object counts. Our experiments reveal that training with single object policies yields the highest sample efficiency, while training all objects together results in lower performance. We also observe that the mix policy achieves the best sim to real transfer success rate, suggesting that overfitting to specific shapes may hinder performance in other setups. Lastly, we investigate the effectiveness of combining different object representations for vision-based sim to real transfer. Our results indicate that using both dense and sparse representations improves transfer success, especially as the importance of full object geometry increases. We evaluate our system's overall capabilities by measuring task success rates across various tasks. We report success rates of 62.3% for grasp and reach, 80% for box lift, and 52.5% for bimanual handover tasks. Our grasp and reach policy demonstrates the ability to generalize to new objects, and we showcase its robustness against force disturbances in our video. We also discuss how our learned policies can be integrated with other systems for more complex tasks, exemplified by a general pick and drop system demonstrated in our video. Section Summary. In this section, we evaluate the effectiveness of our auto-tuned robot modeling and find that it significantly improves sim to real transfer success rates. We also demonstrate that using primitive geometric shapes for object modeling enhances training efficiency and generalization, while our reward design and task-aware hand pose initialization principles lead to robust and dexterous task performance across various scenarios. Section: Limitations. In this section, we explore the main challenges of applying reinforcement learning, RL, to robot manipulation and present practical techniques to address these issues. Using our proposed methods, we create a sim to real RL pipeline that shows a viable way to tackle robot manipulation, demonstrating generalizability, robustness, and dexterity. However, the skills we have achieved are still not on par with the versatile manipulation abilities of humans. There is still much work to enhance each part of this pipeline and fully realize the potential of sim to real RL. For instance, we could improve reward design by incorporating stronger human insights, like task demonstrations from teleoperation. Additionally, there are significant unresolved issues in our work. We do not employ any innovative methods to bridge the sim to real gap in dynamics, relying instead on basic domain randomization. We suspect this may contribute to the low success rate in the bimanual handover task, which is the most dynamic task we tested. Finally, we face limitations due to the lack of reliable hardware for dexterous manipulation. Although we use multi-fingered robot hands, their dexterity is not comparable to that of human hands in terms of active movement capabilities. We believe that the limitations of our learned policies are not due to our approach. and we aim to expand our framework to include more advanced robot hand designs in the future.